David Smith here with one more flipped classroom math lesson. 3 tips before we start. First, remember that you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to jot down some notes or write down some questions for our next class. Lastly, you can turn on the captions so you can read my words go by on the screen. Today's lesson is about quadratic equations and perfect squares. And there's some interesting tricks we can do with those, with our quadratics. So first, let's just talk about what a perfect square is. I'm going to put 2 numbers on the board. You tell me which one is the perfect square. Okay, 2 numbers. Which is the perfect square? 64, because 64 is a single integer squared. So 8 squared makes 64, so 64 is considered a perfect square. 20 is not. It's got a square root, just fine, but it's not going to be an integer. This is also a perfect square, because when it factors down, it makes one thing squared. Now let's just do this as a factoring problem. What 2 numbers multiply to 9 and add to 6? Those 2 numbers are 3. So we could write this one in factored form as x plus 3 times x plus 3. And we've factored it. Now we can simplify this one step further and write it as x plus 3 squared. Now that shows the perfect squareness of this expression. We have x squared plus 3x plus 9. That can be reduced down to one thing. Now our thing, instead of 8 squared making 64, our thing is x plus 3, but x plus 3 squared does indeed make that expression. All right, here's another perfect square. I want you to pause the video and figure out what thing squared makes that quadratic expression. So I did my usual factoring trick. What 2 numbers multiply to 49 that add up to negative 14, and those 2 numbers are negative 7, so this is x minus 7 times x minus 7, which indeed is x minus 7 squared. So that's a quick review of what a perfect square is in a quadratic function. Another quick little review segment. If I have a number, x squared, that equals some value a, then if I take the square root of both sides, I'm trying to isolate my x just to find out what x is, it's going to be plus or minus a. That's because the square root of 4 is plus minus 2. Because we know that minus 2 squared is also positive 4. So that's how this works out. Now if I have a little bit more of a complex expression, x minus h squared equals a, take the square root of both sides, x minus h equals plus or minus a. Whenever you take the square root, you got a plus or minus going on. Then I add h to both sides, and so x in this case is h plus or minus a. So that's mapping out some of the territory that we're going to jump into in just a minute. All right, so now let's solve a quadratic equation for x using what we know about perfect squares. So solve using perfect squares. So check this out. This one is a perfect square, and I got my 11 over here. So I want to find out what values of x in this function are going to make 11. So pause the video and work this perfect square on down. Just bring your 11 on down and stop when you think you've got that done. Okay, so this perfect square ends up being x plus 5 squared. I brought my 11 down. Now I'm going to take the square root of both sides to get x a little bit less encumbered. So I have x plus 5 equals plus minus root 11. Getting closer. Now I subtract 11 from each side. I get x equals negative 5 plus or minus root 11. Now this is an exact answer. Pay attention to the prompts. If the prompt says exact, don't put this root 11 in your calculator and get 2 values. Just leave it as 5 plus or minus root 11. All right, now we're going to do this same problem, but we're going to do it graphically. So if you don't have your graphing display calculator out, you want to go grab that. You're going to need that in a second here. So let's go shoot over here. What we're doing is we can treat this problem as a request to find the points of intersection between 2 functions. So we have one function here, that's our perfect square function, and then we have this other one, y equals 11. And all we're doing here is we're just saying, where does this function equal that function? So another way to say that is, what value of x on this side is also equal to 11? what value of x makes that function equal to 11. So we can do this graphically by finding points of intersection. It's kind of an interesting approach. So what I want you to do, pause the video, get out your calculator, and put in this function and also put in that function. And then use your trace feature to find the points of intersection. All right, here's what I get. Let's take a look at the graph. Here's my function, the x squared plus 10x plus 25. As expected, that makes a nice little parabola. Check this out. Back over here, this looks like a part of vertex form. And if you thought that, you are right. So that means that the x-coordinate of the vertex is -5. And that comes up here. That would be the point -5, 0. Okay? So that's kind of a confirmation from what we know before that that graph is correct. It lines up and makes sense. So then I graphed my line y equals 11. And so that's a horizontal line at the point 11 up from the x-axis. And then I can use a trace feature on the calculator to find the x-coordinate of the points of intersection. And so here, the x-coordinate is -8.32, and the x-coordinate on this one is -1.68. Now notice how I have 3 sig figs. Remember, that's a standard, that's an IB standard. Whenever you write decimals down, you want 3 significant figures. And I want you to see what you can do to tie this to that. So this is a critical thinking question I'm asking you. Could you use this to verify that or that to verify this? Pause the video, pull out your calculator, do some calculations, see what you get. All right, here's the thing. If you do -5 plus root 11, you're going to get -1.68. If you do -5 minus root 11, you're going to get -8.32. So this is 2 ways to find solutions to this equation. We did it graphically by thinking about points of intersection between this function and that function. And then we also did it algebraically by using our completing the square and solving for x. So these are 2 approaches to that. So what you want to do is pay attention to your prompts. However, if you're prompted to do it this way, you can also graph it to confirm your answer from this way and vice versa. All right, let's do this again. This time I'm going to turn you loose. I want you to take it as far as you can before you come back. So here is my quadratic, perfect square. I want you to go ahead and algebraically find the solutions to this side of the equation that make it equal 8. So pause the video and do your algebra. All right, here we go. Here's my perfect square. That factors down into x minus 2 squared. I bring my 8 down. Now I'm going to take the square root of both sides. X minus 2 equals plus or minus 8. Now I'm moving my 2 over, and I simplified my root. You need to do that. The square root of 8 can be written as 2 root 2. If you need help remembering how to do that, let me know. I've got video links I can send you. So my solution here, my exact solution, leaving the root 2 in place, is x equals 2 plus or minus twice the square root of 2. So that's my solution to making this side of the quadratic equal to 8. Now I want you to pause the video and do the same thing graphically on your graphing display calculator. All right, let's see how you did. Check this out. Here's my right-hand side. That's the y equals 8. And that's just a vertical line, or a horizontal line, pardon me, going through the point y equals 8, or 0, 8, going through the y-intercept there. And then here's my parabola, graphed x squared minus 4x plus 4. The vertex is at 2, 0. That's confirmed by here. We changed that sign to plot our vertex, so that's good. And then I use my trace function on my graph, on my calculator, to find out that the x-coordinate of this intersection point is minus 0.828, and the x-coordinate here is 4.83. Now to confirm this, if you feel like you'd like to try that, go ahead and do 2 plus 2 root 2. That should give you 4.83. And do 2 minus 2 root 2. That should get you the minus 8.28. 3 significant figures. Don't forget that. All right, this lesson also includes some stuff that doesn't relate to perfect squares. I'm not sure why the IB, or it's not the IB, it's our textbook writer, put these 2 concepts in here in a section that's called quadratic equations and perfect squares. So we just have to write it through this way. I think I might organize the material differently, but I am not a textbook writer, so I'm not going to go there. So here we go. What we're doing is I added this little subtitle to our title. We're going to find points of intersection of the graphs of this function, 4x squared minus 2x minus 5, and this function, 3x plus 2. Notice how I put GDC there. This question is a graphing display calculator question. So what I want you to do, I think you have enough already to just go do that. Now I'm going to add one requirement, sketch graph, okay? So I want you to go ahead and use the calculator. You can use your trace to find those intersection points, but I also want you to make a graph sketch of that and then come back and compare your results. Let's see how you did. So first off, here's my linear function, 3x plus 2. That's this upward sloping line. I could label my intercept there. That's the point 0, 2, because we know that from slope-intercept form, right like that. And then I have my quadratic function, 4x squared minus 2x minus 5. That's this parabola right there. And then it intersects my line in two spots. I use my trace function, and I listed my points of intersection right here, both of them to 3 significant figures. Remember to practice that. That is worth points on a test. All right, so check this out. Important to pay attention to the prompt. Solve minus 3.6x squared plus 5.4x minus 2 equals 1.8x minus 7.2 on the GDC. So this is where we're going to consider this from a points of intersection concept. So we want a value of x that makes this quadratic expression equal to this linear expression, okay? Now you could move these terms over, set equal to 0, and solve for x-intercepts, and that would work. But what they're asking to do is, in this way, use it as finding a point of intersection. So I'm going to add this little command right there, sketch graph. You might see them say, show solutions on graph. Okay, so whatever that prompt is, you need to make sure you dissect it so you know what you need to do to earn the points. Okay, so I think you have what you need. This is similar to that last example. I want you to pause the video, go ahead and create your graph for that, and then come back when you're done. Let's see how you did. Let's start with the linear function. This is my upward sloping graph for 1.8x minus 7.2. Notice how I get my y-intercept for free. That's the point here, 0 minus 7.2. So I went ahead and put that on there. Strictly speaking, this is a graph sketch, so you're not required to label every single point. I just like to be thorough. And then let's take a look at our quadratic function. This is a downward opening parabola. I can confirm that. It also has a y-intercept, and that is the point 0 minus 2. So I went ahead and labeled that right there. And then I used my trace function on my graph to figure out the x-coordinates of the points of intersection. And remember, the x-coordinates are the solutions to this equals this. So I went ahead and labeled them on my graph, and then I went ahead and used my curly brackets to show my two solutions, which is a standard notation for that. Not an absolute requirement, but if you do this problem, you do want to clearly indicate that these two values are the solutions to this function. Now that you've watched the video, jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that challenged you the first time. If you enjoyed the video, please click like. If you'd like to help me grow my YouTube channel, please click subscribe.